Okay, welcome everybody to proving quadrilaterals are parallelograms. In the last video, we were looking at certain characteristics of parallelograms. This time, we're going to do the converse of that, to say that if we have certain characteristics, it would prove that the quadrilateral is a parallelogram. Okay, so the opposite sides theorem converse states, if the opposite sides of a quadrilateral are congruent, then the figure is a parallelogram. So here's a sketch. We know opposite sides are congruent, and it's a parallelogram. The opposite angles theorem converse states if the opposite angles of a quadrilateral are congruent, then the figure is a parallelogram. And whoops, I misspelled parallelogram here. Let me fix that. Okay, and now let's make a sketch of the opposite angles theorem converse. Okay, and there it is. Now the consecutive angles theorem converse states if the consecutive angles of a quadrilateral are supplementary, that means they add up to 180, then the figure is a parallelogram. So I'm going to make a quadrilateral here with consecutive angles, let's say 45 and 135. So we know that that's a supplementary pair there. Okay, let's look at the next one. The parallelogram diagonals theorem converse. So if the diagonals of a quadrilateral bisect each other, then the figure is a parallelogram. So when they bisect, that means that the two diagonals share the same midpoint. Okay, let's take a look at example 1. Write a two-column proof, and we have a given statement there, and we're trying to prove that this quadrilateral is a parallelogram. So the given statement is that segment AB is parallel to segment DC, and that segment AB is congruent to DC. So let's update the drawing. Now I know that angle ABD is congruent to angle CDB, because I have these two parallel segments and this transversal. So that is the alternate interior angle postulate there. Okay, so look, we've got two triangles here. I can show that these two are congruent, but I need one more piece, and that is another side. I know that segment DB is congruent to segment DB, because that is the reflexive property of congruence, and let's mark that on the drawing. So look, I know that I have a side, corresponding side, and an angle in another side. So I can show that triangle ABD is congruent to triangle CDB because of SAS. Well, now I know that segment AD is congruent to segment CB because we've already proven the triangle's congruent, so that would just be CPCTC. And now I can say that quadrilateral ABCD is a parallelogram because of the opposite sides theorem converse, which is the theorem that we just learned in the very beginning, which states if we know the opposite sides are congruent, then the figure is a parallelogram. Okay, we got that one. Moving on. The parallelogram theorem. Okay, so if a quadrilateral has one set of parallel sides that are also congruent, then the figure is a parallelogram. And this is just what we proved in the last example. One set is parallel and congruent. Okay, example 2 is quadrilateral EFGH parallelogram. In the first one, we know it's yes because the opposite angles converse, or the consecutive angle theorem converse. Part B, it's no, the diagonals do not bisect. Okay, example 3, what value of x would make ABCD a parallelogram? Well, it's given that segment AB is parallel to DC. Therefore, if AB is congruent to DC, then ABCD would be a parallelogram from the parallelogram theorem that we just did above. So we need to make AB congruent to DC. So I can substitute the expressions in, and I get 5x minus 8 equals 2x plus 13. And I need to figure out what value of x will make this true. So I need to solve for x just using some simple algebra, and I get x equals 7. So x must equal 7 in order for this figure to be a parallelogram. Example 4 is the quadrilateral ABCD a parallelogram. Explain the different ways you could prove this quadrilateral is a parallelogram using the theorems above. Okay, so the first thing we could do is compare the slopes. If the opposite sides have congruent slopes, then it's a parallelogram. 2, we could use the distance formula to check if the opposite sides are congruent. 3, we could use the midpoint formula to see if the diagonals bisect each other. 4, we can find the distance and slope of one pair of sides and see if that works. So here are the formulas that we will need to use for this problem, with slope, distance formula, maybe the midpoint formula. Well, let's try number 4. So I have to do a combination of finding the distance and slope. So I'm going to write down the coordinates here for A, B, C, and D. Let's find the distance of segment AB, and then we'll find the distance of segment DC, and then we'll also compare the slopes. So I'm going to write for point A, I'm going to call this x1, y1, and B would be x2, y2. I'm going to substitute my coordinates in here using the distance formula. Simplify this a little bit. I get the square root of 4 squared plus negative 2 squared, which is root 16 plus 4, which is root 20, which simplifies to 2 root 5. Now let's take a look at the slope here. Slope is rise over run. I could use the y2 minus y1 over x2 minus x1. But let's take a look at it graphically, visually here. If I'm at point A, what do I need to do to go down and over to point B? Well, I need to go down 2, and then I'm going to run 4. So going down 2 is a negative 2, and over 4 is a positive 4. That simplifies to negative 1/2. So my slope is negative 1/2. Now let's compare the distance for DC. Find the distance for DC, which is opposite of AB, and the slope as well. So I'm going to use the distance formula again. x2 minus x1 squared plus y2 minus y1 squared. And you'll see when I simplify this, I get 2 root 5, which is the same as the distance for AB. The slopes we can also do visually, and I go down 2 over 4. So the slopes are the same, the distances are the same, therefore AB and DC are parallel, and ABCD is a parallelogram. Well, that's it. I hope this makes sense.